What if I told you that every photon of light that has ever touched your skin contains a permanent, unbreakable record of that interaction? That the sunlight streaming through your window right now isn't just energy, it's a cosmic filing system that has been storing information since the beginning of time itself? Here's something that will absolutely shatter your understanding of reality. In 2019, physicist Stephen Barnett at the University of Strathclyde made a discovery that turned quantum physics on its head. He found that photons, those tiny packets of light, don't just carry information. They potentially store it in a way that might be fundamentally impossible to erase. Not difficult, not impractical, impossible. Think about what that means for just a moment. The light bouncing off this screen and entering your eyes right now, it's been modified by that interaction in a way that could theoretically be traced back, like a cosmic fingerprint that never fades. The sunlight that warmed the dinosaurs 65 million years ago might still contain encoded information about those ancient creatures, scattered across the universe in patterns we're only beginning to understand. But here's where it gets truly mind-bending. If light stores quantum information permanently, then the universe isn't just expanding, it's becoming an ever-growing library of everything that has ever happened. Every interaction, every moment, every choice you've ever made might be encoded in photons spreading outward at the speed of light, creating a permanent record that cannot be destroyed. Before we dive deeper into this rabbit hole, I need you to do something. Hit that like button and subscribe, because what you're about to learn will fundamentally change how you see the world around you. And drop a comment telling me what country you're watching from and what time it is where you are, because by the end of this video, you'll understand why that information itself is now encoded in light particles in a way that might persist forever. Let's start with what seems like a simple question. What is light, really? You probably learned in school that light is both a wave and a particle, the famous wave-particle duality. But that explanation, while technically correct, barely scratches the surface of how weird light actually is. Think of it like this. Imagine if water could be both an ocean wave and a single drop of water at the same time, and which one it was depended on whether you were looking at it. That's already strange, right? But light is so much stranger than that. In 1905, Albert Einstein won his Nobel Prize not for relativity, most people get this wrong, but for explaining the photoelectric effect, which proved that light comes in discrete packets called photons. Each photon is like a tiny messenger, carrying energy from one place to another. But here's the twist that Einstein himself found disturbing. These photons don't just carry energy. They carry information about every interaction they've had since they were created. Now, you might be thinking, okay, so light carries information. My Wi-Fi router does that. What's the big deal? But quantum information is fundamentally different from the information in your phone or computer. Classical information, the kind we're familiar with, can be copied, deleted, and measured without changing it. You can read this sentence, and the sentence doesn't change because you read it. Quantum information doesn't work that way. In 1982, physicist William Wouters and his colleague Wojciech Zurek proved something called the no-cloning theorem. This theorem, which is mathematically ironclad, states that you cannot make a perfect copy of an unknown quantum state. It's not that we don't have the technology, yet it's that the laws of physics themselves forbid it. Think of it like trying to photocopy a shadow that disappears when you turn on the light to copy it. But here's where it gets interesting. If you can't copy quantum information, what happens to it? Does it just vanish? Can it be destroyed? This brings us to one of the most profound principles in all of physics, unitarity. This principle, which emerged from the work of John von Neumann in the 1930s, states that information in a quantum system cannot be destroyed. It can only be transformed. It's like a cosmic conservation law, but instead of conserving energy or momentum, it conserves information itself. Let me give you an analogy. Think of quantum information like a deck of cards that's been shuffled. No matter how thoroughly you shuffle that deck, all 52 cards are still there. You haven't destroyed any cards. You've just rearranged them. In principle, if you knew exactly how the deck was shuffled, you could reverse the process and restore the original order. Quantum information works the same way in principle. No information is ever truly lost, just scrambled in increasingly complex ways. Now, photons are special in this quantum world. Unlike electrons or atoms, which have mass and can be trapped and controlled, photons are restless travelers. They're born moving at the speed of light, and they never slow down, never stop, never rest until they're absorbed by something. Every photon that hits your eye and allows you to see was created somewhere, maybe in the sun, maybe in a light bulb, and has been traveling since that moment of creation. What will absolutely blow your mind is this. During that journey, every single interaction that photon has every reflection off a mirror, every pass through a lens, every near miss with an atom potentially leaves a mark on its quantum state. The photon carries a record of its entire history, encoded in properties like its polarization, phase, and frequency. In 2011, a team led by physicist Anton Zeilinger in Vienna demonstrated something remarkable. They showed that photons could be entangled with other particles in ways that create correlations across vast distances, correlations that Einstein famously called spooky action at a distance. But what Zeilinger's team found was even spookier. These entangled photons maintain their correlations even after traveling hundreds of kilometers. The information about their entangled state doesn't degrade or disappear, persists. So here's where we are so far. Light comes in particles called photons. These photons carry quantum information that cannot be cloned. The laws of physics suggest this information cannot be destroyed, only transformed. And photons can maintain complex quantum states over vast distances and potentially vast times. But this raises an uncomfortable question that's been bothering physicists for decades. If quantum information cannot be destroyed, and photons carry quantum information wherever they go, then what happens to all that information? Where does it go? And most disturbingly, does it ever truly disappear? Here's something that will make you question everything you thought you knew about observation itself. The act of measuring quantum information fundamentally changes it. But does it destroy the information? Or just transform it in ways we can't easily trace? This is called the quantum measurement problem, and it's been driving physicists crazy since the 1920s. Let me explain why it matters for our question about whether light stores information forever. When you measure a photon, say, by checking its polarization with a polarizing filter, something truly bizarre happens. Before the measurement, the photon exists in what's called superposition of states. Think of it like a coin spinning in the air. It's neither heads nor tails, but somehow both possibilities at once. But the moment that coin lands, or the moment you measure the photon, it suddenly chooses one definite state. Niels Bohr, one of the founding fathers of quantum mechanics, argued that before measurement, it's meaningless to even say the photon has a definite polarization. The act of measurement doesn't reveal a pre-existing property. It creates that property. This is called the Copenhagen interpretation, and it dominated physics for decades. But here's what kept Einstein up at night, and what should disturb you too. If measurement creates reality rather than revealing it, what happened to the information about all those other possibilities that didn't manifest? Did it vanish? Did you just destroy information by measuring the photon? In the 1950s, physicist Hugh Everett proposed a radical solution that sounds like science fiction but is taken seriously by many physicists today. He suggested that nothing is actually destroyed. When you measure that photon's polarization, the universe splits into branches, one where you measured horizontal, one where you measured vertical. All the information is preserved, just distributed across multiple universes. I know what you're thinking. That sounds insane, and you're right to be skeptical. But here's what's truly mind-bending. The mathematics of quantum mechanics naturally leads to this conclusion. The equations don't show information being destroyed during measurement. They show it becoming entangled with the measuring device, the environment, and ultimately everything the measurement interacts with. This process is called decoherence, and it was worked out in detail by physicist Wojciech Zurek in the 1980s. Think of it like this. Imagine you write a secret message in the sand on a beach. When the waves come in, your message isn't destroyed. It's still there in principle, encoded in the positions of trillions of individual grains of sand. But from a practical standpoint, the information has become so scrambled and spread out that retrieving it would be virtually impossible. And this is crucial, virtually impossible is not the same as fundamentally impossible. In 2012, physicist Ephraim Steinberg at the University of Toronto did something that seemed impossible. His team used a technique called weak measurement to track the paths of photons through a double-slit experiment without destroying their wave-like interference pattern. They essentially found a way to peek at quantum information without completely collapsing it. What Steinberg's experiment revealed was profound. The information about the photon's path doesn't vanish when you measure it. It gets distributed between the photon and the measuring device in a way that preserves the total amount of information in the system. It's like breaking a mirror into 1,000 pieces. The reflection is still there, just fragmented and scattered. So when a photon interacts with an atom, or passes through your eye, or hits a detector, the quantum information it carries doesn't disappear. It becomes entangled with whatever it interacted with. The photon might be absorbed and cease to exist as a separate particle, but the information it carried is now encoded in the atom, in the molecules of your retina, in the electrons of the detector. Here's the question that should be echoing in your mind right now. If that information never truly disappears, just gets distributed and entangled with more and more systems, then does it exist forever? Is the entire universe becoming an ever-growing web of entangled information, with photons serving as the primary messengers that spread this information throughout space and time? Before we answer that, we need to talk about something that confused even Einstein, something that suggests the universe might have a memory far more profound than we ever imagined. What if I told you that particles of light that have never met and are separated by billions of light years can share information instantaneously? And that this isn't speculation, it's been proven in laboratories thousands of times? This is quantum entanglement, and it's the phenomenon that Einstein couldn't accept, even though his own equations predicted it. In 1935, Einstein, along with Boris Podolsky and Nathan Rosen, published a famous paper arguing that quantum mechanics must be incomplete because it predicted this spooky action at a distance. Here's what bothered Einstein. According to quantum mechanics, you can create two photons in a special entangled state. Then you can separate these photons by any distance across a room, across a galaxy, across the entire observable universe, and they remain connected. When you measure one photon and find it has, say, vertical polarization, the other photon instantly has horizontal polarization, no matter how far away it is. Einstein thought this meant that quantum mechanics was missing something that there must be hidden variables that predetermined what each photon would do, like secret instructions written inside them before they separated. But here's what will blow your mind. In 1964, physicist John Stewart Bell proved mathematically that no theory of hidden variables could reproduce all the predictions of quantum mechanics. And in 1982, Ailing Aspect conducted experiments in Paris that definitively showed Einstein was wrong. The entanglement is real. The correlations between separated photons are genuinely instantaneous and cannot be explained by any information the photons carried with them when they separated. Think about what this means. Two photons become entangled. Let's say they're created in your lab on Earth. You send one photon to the moon. The other stays in your lab. When you measure your photon on Earth, something about the photon on the moon changes instantly, 240,000 miles away, faster than light could possibly travel that distance. Now, Before you start thinking you can use this to send messages faster than light, here's the catch. You can't control what result you get when you measure your photon. It's random. So while the correlation between the photons is instantaneous, you can't use it to transmit information in the conventional sense. But, and this is key, it does mean that information is shared between the photons in a way that transcends space and time as we normally understand them. In 2017, a team of Chinese physicists led by Jianwei Pan successfully demonstrated quantum entanglement between photons on Earth and a satellite in space, over a distance of more than 1,200 kilometers. The entanglement persisted. The information shared between these photons remained intact despite the vast distance. But here's where this connects to our central question. If photons can remain entangled over vast distances, and if quantum information cannot be destroyed, only transformed, then what happens over vast times? Do photons maintain their quantum information indefinitely? To understand this, we need to talk about something called quantum coherence. Think of coherence like a group of musicians playing in perfect sync. As long as they maintain that synchronization, you can hear the harmony. But if even one musician drifts slightly off beat, the coherence starts to break down. Eventually, if everyone's timing is off, you just hear noise instead of music. Photons maintain quantum coherence remarkably well because they don't interact strongly with most things. A photon traveling through empty space can maintain its quantum state for billions of years because there's nothing to disturb it. The information it carries encoded in its polarization, its phase, its frequency, persists throughout its journey. But space isn't perfectly empty. There's the cosmic microwave background radiation photons left over from the Big Bang. There's the occasional atom of hydrogen. There's dark matter that we don't fully understand. Each potential interaction is an opportunity for that photon's quantum state to become entangled with something else in the universe. And here's what should make your mind explode. Every time a photon becomes entangled with something, the information it carries doesn't disappear. It spreads. It becomes part of a larger web of quantum correlations that spans the cosmos. In 2015, physicist Leonard Susskind at Stanford proposed something called quantum complexity as a new way of thinking about information in the universe. He argued that even when information becomes so scrambled that it appears lost, like when it falls into a black hole, it's not actually destroyed. Instead, the complexity of the quantum state just keeps growing, making the information exponentially harder to retrieve, but never truly impossible. Think of it like this. Imagine you have a library with every book ever written, but someone has randomly redistributed every single letter from every single book across all the pages. The information is still there. Every letter is accounted for, but reconstructing the original books would require computational resources beyond anything we can imagine. This is what happens to the information carried by photons over cosmic timescales. It doesn't disappear. It doesn't get destroyed. It becomes woven into the quantum fabric of the universe in increasingly complex ways. But now we need to confront something that seems to contradict everything I've just told you. Something that physicist Stephen Hawking spent decades trying to resolve. What happens when photons encounter the ultimate point of no return? A black hole. Picture this. A photon that has traveled for billions of years, carrying quantum information about ancient stars and galaxies, approaches a black hole. It crosses the event horizon, that point of no return where gravity is so strong that not even light can escape. What happens to the information that photon carried? For decades, physicists thought the answer was simple. The information is lost forever, crushed into the singularity at the black hole's center. But in 1974, Stephen Hawking dropped a bombshell that created what became known as the black hole information paradox, possibly the deepest crisis in theoretical physics. Hawking discovered that black holes aren't actually black. They emit radiation now called Hawking radiation, due to quantum effects near the event horizon. Think of it like this. The vacuum of space isn't truly empty. It's constantly bubbling with pairs of virtual particles that pop into existence and annihilate each other almost instantly. But near a black hole's event horizon, one particle from the pair might fall into the black hole while the other escapes. The escaping particle becomes real, and the black hole loses a tiny bit of mass. Here's the problem. Hawking's calculations showed that this radiation is completely thermal, meaning it's random, like the heat from a fire. It carries no information about what fell into the black hole. So if you throw a photon carrying quantum information into a black hole, and the black hole eventually evaporates through Hawking radiation, where did that information go? According to the principle of unitarity that we discussed earlier, quantum information cannot be destroyed. But Hawking's calculation suggested it was destroyed. This contradiction, the information paradox, tormented Hawking for the rest of his life. In 1997, Hawking made a bet with physicist John Preskill about whether information is lost in black holes. Hawking bet that it was lost. Preskill bet that it was preserved. The stakes? An encyclopedia of the winner's choice, from which information can be recovered at will. Fast forward to 2004. Hawking conceded the bet. Why? Because of breakthroughs in string theory and quantum gravity that suggested information isn't lost, it's encoded on the black hole's event horizon in a holographic form, then eventually released in the Hawking radiation in a highly scrambled form. But here's what will truly blow your mind. In 2019, physicist Jeff Pennington at Stanford, along with several colleagues, essentially solved the information paradox using new mathematical tools. They showed that information does escape from black holes, but in such a scrambled form that you'd need to collect more than half of all the Hawking radiation the black hole ever emitted to start reconstructing what fell in. Think about what this means for our photon. Even in the most extreme case falling into a black hole, its quantum information isn't destroyed. It's transformed, scrambled beyond recognition, but fundamentally preserved. The universe refuses to forget. Leonard Susskind calls this the holographic principle, the idea that all the information about three-dimensional space can be encoded on a two-dimensional surface, like a hologram. In the case of a black hole, all the information about everything that ever fell in is encoded on its surface, the event horizon. But black holes eventually evaporate. Where does the information go then? This brings us to something even stranger. In 2016, Hawking and his colleagues proposed that black holes have soft hair, a layer of zero-energy particles at the event horizon that store information about everything that fell in. When the black hole evaporates, this information is released back into the universe through the Hawking radiation. Let me give you an analogy. Imagine burning a book. The book appears destroyed, but in principle, if you could track every single molecule in the smoke, every photon in the flames, every quantum of heat that radiated away, you could reconstruct the book. The information wasn't destroyed, it was converted into an incredibly complex pattern in the environment. The same thing happens with black holes. The information carried by our photon, even after falling past the event horizon, is eventually released back into the universe in the Hawking radiation. It's scrambled in the most complex way possible, but it's not destroyed. Here's what should make you pause. If information cannot be destroyed, even in the most extreme gravitational environment in the universe, then it really cannot be destroyed anywhere. The quantum information carried by light is truly permanent. But this raises a disturbing question. If the universe is constantly accumulating information, never forgetting anything, then isn't it becoming increasingly complex? Isn't there a limit to how much information can be stored? Actually, there is a limit. And understanding this limit reveals something profound about the nature of reality itself. What if I told you that there's a maximum amount of information that can be stored in any region of space, and that this limit is determined not by the volume of that region, but by its surface area? This sounds like bizarre theoretical speculation, but it's one of the most well-established results in modern physics. In 1972, physicist Jacob Bekenstein made a revolutionary discovery. He was a graduate student working with John Wheeler at Princeton, trying to understand black holes. Wheeler had posed a challenge. If you could throw anything into a black hole, books, computers, whatever, and the black hole just got slightly bigger, couldn't you violate the second law of thermodynamics by hiding entropy inside the black hole? Bekenstein realized something profound. Black holes must have entropy, and entropy in physics is fundamentally related to information. Specifically, entropy measures the number of possible microscopic states a system could be in while looking the same from the outside. But here's the kicker. Bekenstein calculated that a black hole's entropy is proportional to the area of its event horizon, not its volume. Think about how weird this is. Normally, we think of information storage as a three-dimensional thing. A hard drive stores data throughout its volume. Your brain stores memories in its volume. But black holes, and by extension, any region of space according to the holographic principle, store information on their surface. The Bekenstein bound, as it's now called, tells us the maximum information that can be stored in any spherical region of space. And that maximum is proportional to the region's surface area measured in Planck. Units tiny squares about 10 to 35 meters on a side. Let me make this concrete. A sphere the size of your head can store a maximum of about 1,069 bits of information. That sounds like a lot, and it is far more than your brain actually stores. But it's not infinite. There's a hard limit written into the fabric of space-time itself. Now, here's where this connects to our photons. Every photon that carries information through the universe is subject to this limit. The universe itself has a maximum information capacity. If we assume the observable universe is a sphere with a radius of about 46 billion light years, the Bekenstein bound tells us it can store at most about 10,123 bits of information. That's a genuinely enormous number, more than a googol raised to the power of a googol. But it's finite. The universe cannot remember everything about every quantum interaction that has ever occurred. Something has to give. So what happens when you approach this limit? Does old information get erased to make room for new information? Does the universe experience something like memory loss? Here's the truly mind-bending part. We don't know for sure, but there are fascinating possibilities. One idea, proposed by physicist Tom Banks in 2000, is that the cosmological constant, the mysterious dark energy that's accelerating the expansion of the universe, might be related to this information limit. Think of it like this. As the universe expands, the maximum amount of information that can be stored increases because there's more surface area at the cosmic horizon. Dark energy drives this expansion, effectively creating more storage space for quantum information. In this view, the universe isn't just expanding, it's constantly increasing its information capacity to accommodate all the quantum interactions happening within it. But photons play a special role in this cosmic information system. Unlike matter particles that clump together due to gravity, photons spread out, carrying information away from where it was created. Every time a star burns, it sends photons radiating in all directions, distributing information about that star throughout an ever-growing sphere. In 2018, physicist Raphael Bousso at Berkeley refined the holographic principle into what he calls the covariant entropy bound. This principle says that information flows through space-time in a very specific way, and that light rays form the boundaries of these information flows. Photons, in this view, are the primary carriers of information in the universe, and the pattern of light rays throughout space-time determines how information is distributed. Here's what should make your brain hurt. If photons are the primary information carriers, and if information cannot be destroyed, then the pattern of light rays throughout the entire history of the universe forms a kind of permanent record. This record is distributed across the cosmic horizon in a holographic form, and in principle, everything that has ever happened could be reconstructed from it. But there's a catch, and it's a big one. Reconstructing this information would require computational resources beyond imagination. It's not just about having a big enough computer. The computation itself would require more time and energy than exists in the observable universe. So the information is preserved, but it's effectively inaccessible. It's like having a book written in a code that would take longer than the age of the universe to decrypt, even if you used every atom in existence as part of your computer. This leads us to a profound distinction. Information can be preserved in principle while being irretrievable in practice. The photons that have carried quantum information since the beginning of time still remember everything in some sense. But that memory is encoded in a form so complex that it might as well not exist for any practical purpose. But before you think this makes the question trivial, consider this. Practical purposes depends on your perspective. For beings with sufficient technology and time hypothetical advanced civilizations, billions of years in the future, or perhaps the universe itself, this information might not be inaccessible at all. Which brings us to an even stranger question. What if the universe itself is doing the computation? What if every quantum interaction, every entanglement between photons and matter, is a step in a vast cosmic calculation that processes and stores information in ways we're only beginning to understand? Here's something that will fundamentally reshape how you think about reality. The universe might not just store information, it might be information. And every photon, every particle, every quantum interaction might be a computational step in the largest calculation ever conceived. This isn't New Age mysticism or philosophical speculation. It's a serious scientific proposal that emerged from some of the deepest insights into quantum mechanics and information theory. In 2002, MIT physicist Seth Lloyd published a groundbreaking paper calculating how many computational operations the universe has performed since the Big Bang. His answer? About 10,120 operations so far. Every quantum interaction, every particle collision, every photon absorption, every moment of quantum entanglement is a computational step. The universe is, in a very real sense, computing itself. Lloyd's insight builds on earlier work by physicists like Richard Feynman, who in the 1980s proposed that quantum systems could be used as computers that would be exponentially more powerful than classical computers. But Lloyd took this further. If quantum systems naturally perform quantum computations, then isn't the entire universe just one massive quantum computer, constantly calculating its own evolution? Think of it like this. When a photon travels from a star to your eye, it's not just passively carrying information. It's actively processing that information through its interactions with the quantum vacuum, with magnetic fields, with gravitational potentials. Each of these interactions is a quantum operation that transforms the photon's state in specific ways governed by the laws of physics. But here's what will truly blow your mind. According to quantum mechanics, a photon doesn't follow just one path from the star to your eye. It simultaneously explores all possible paths, and then the different paths interfere with each other in a process called quantum interference. This is what gives light its wave-like properties. The photon is effectively computing which path to take by exploring all paths simultaneously, a fundamentally quantum form of parallel processing. In 1965, Richard Feynman developed a mathematical framework for this called path integrals. Every photon, in traveling from point A to point B, can be thought of as taking every possible path through space-time simultaneously, with each path contributing to the final probability of where the photon ends up. It's like the universe is running countless simulations in parallel to determine what actually happens. Now, here's the connection to information storage. If the universe is computing itself, then the information isn't just stored in the particles. It's stored in the process of computation itself. The history of every photon's journey isn't just a record of where it went. It's a record of every possible path it could have taken and how those possibilities interfered with each other. This means that quantum information is stored not just in states, like the photon is polarized vertically, but in processes, like the photons, Polarization evolved in this particular way due to these specific interactions. The full information content includes both what is and what could have been. In 2016, physicist Chiara Maroletto at Oxford proposed a new way of thinking about physics based entirely on information and counterfactuals, what could or couldn't happen, rather than just what does happen. In her framework, the laws of physics are fundamentally about which transformations of information are possible and which are impossible. Photons, as the primary carriers of information, are central to this picture. But here's where it gets really wild. If the universe is computing itself, and if photons are carrying out quantum computations as they travel, then those computations might be irreversible in a specific sense. Not in the sense that information is destroyed. We know that doesn't happen. But in the sense that the computational path taken to get to a particular state becomes part of the information stored in that state. Let me give you an analogy. Imagine you're solving a Rubik's Cube. You can get to the same final solved state through many different sequences of moves. But if I told you not just the final state, but the exact sequence of moves you used to get there, I'd be giving you much more information. The universe works similarly. The information in a photon includes not just its current quantum state, but the history of computations that led to that state. This has profound implications. It means that two photons with identical current quantum states might actually carry different information if they have different histories. The universe remembers not just what is, but how it came to be. In 2020, a team led by physicist Nicole Younger-Halpern at Harvard explored what they call quantum complexity, a measure of how many quantum operations would be needed to prepare a particular quantum state from a simple starting state. They found that quantum complexity always increases over time, even when entropy stays constant. The universe is becoming computationally more complex, even if it's not becoming more disordered. This gives us a new perspective on our original question. Do photons store quantum information forever? The answer might be yes, but the nature of that storage is more profound than we initially imagined. The information isn't just passively sitting there like data on a hard drive. It's actively being processed, transformed, and woven into ever more complex quantum computations that span the entire universe. Every photon that has ever been emitted since the Big Bang is part of this cosmic computation. The ones that traveled unimpeded through intergalactic space. The ones that scattered off dust clouds. The ones absorbed by your retina right now as you watch this video. Each one carried a thread of quantum information through space-time, and each interaction was a computational step that contributed to the universe's ongoing calculation of its own state. But this raises a question that should send shivers down your spine. If the universe is computing itself, what is it computing? Is there a purpose to this cosmic calculation? And could we, as conscious beings made of matter that processes information, be part of the universe's way of knowing itself? Before we explore those philosophical depths, we need to address something more immediate and practical. Can we actually access this information that photons carry? Can we read the universe's memory? Take a moment to let that sink in. The universe is a vast quantum computer, and light is its primary programming language. Every photon is a packet of executable code, carrying not just data, but processing instructions written into the fabric of reality itself. Now, if you're still with me, you deserve to know something even more mind-bending. Because while everything I've told you so far might seem abstract and theoretical, there are people right now today trying to actually read the information that ancient light has been storing since the dawn of time. And they're succeeding in ways that would have seemed like magic just a decade ago. Hit that subscribe button if you want to see where this goes, because we're about to cross from theory into applications that will change your life. Drop a comment if you're starting to see the universe differently, because by the end of this video, there will be no going back to your old way of seeing reality. What if I told you that scientists have already begun reading information from light that's been traveling for billions of years? that we're essentially accessing the universe's memory by carefully analyzing the quantum properties of ancient photons? This isn't science fiction. It's happening right now, and it's revolutionizing our understanding of cosmic history. Consider the cosmic microwave background radiation photons that have been traveling since about 380,000 years after the Big Bang, when the universe finally cooled enough for light to travel freely. These photons are about 13.8 billion years old. They've been journeying through space for longer than Earth has existed, longer than our sun has been burning, carrying information about the infant universe encoded in their properties. In 2003, NASA's Wilkinson Microwave Anisotropy Probe, WMAP, created the most detailed map of this cosmic microwave background ever made at that time. But here's what's truly remarkable. The information these photons carry isn't just about their energy or frequency. It's encoded in their polarization, the orientation of their electromagnetic waves. Physicist Brian Keating, who worked on experiments to detect primordial gravitational waves, explained that the polarization of cosmic microwave background photons carries information about the density fluctuations in the early universe. These fluctuations eventually grew into galaxies, stars, planets, and ultimately us. The information was encoded in those photons 13.8 billion years ago and has persisted, unchanged, throughout their entire journey. Think about what this means. When you detect one of these photons with a radio telescope, you're accessing a memory that has been stored in quantum form for longer than most atoms in your body have existed. The universe truly doesn't forget. But it gets even more extraordinary. In 2014, the BICEP 2 experiment at the South Pole claimed to have detected a specific pattern in the polarization of cosmic microwave background photons called modes, swirling patterns that would have been imprinted by gravitational waves from the first tiny fraction of a second after the Big Bang. While that particular claim turned out to be complicated by foreground contamination from our own galaxy, the fact that we can even attempt to read such information is stunning. We're trying to access quantum information that was encoded in photons when the universe was 10 to 35 seconds old. Now, let's bring this closer to home. Every photon from every star carries information about that star encoded in its spectrum, the specific frequencies of light it emits. When you split starlight with a prism or a spectrograph, you see dark lines at specific wavelengths. These are called absorption lines, and they're caused by atoms in the star's atmosphere absorbing specific frequencies. Here's the mind-bending part. Those absorption patterns are quantum mechanical processes. An electron in a calcium atom, for instance, can only absorb photons with very specific energies that correspond to the exact energy difference between its quantum states. When you see a calcium absorption line in the spectrum of a star 1,000 light-years away, you're seeing information about a quantum interaction that happened 1,000 years ago, an electron absorbing a photon in a very specific quantum transition. That information has been stored in the remaining photons that make up the star's light, carrying forward through space for a millennium, and is now entering your detector, perfectly preserved. But in 2017, something even more remarkable was discovered. Astronomers using the Alea telescope array in Chile found that they could detect information about the magnetic fields in distant galaxies by analyzing the polarization of light from those galaxies. Magnetic fields affect the polarization of photons passing through them, a quantum mechanical process called Faraday rotation. By analyzing the polarization of photons that have traveled for billions of years, scientists could reconstruct the magnetic field structures of galaxies as they existed billions of years ago. The quantum information about those magnetic fields had been encoded in the photons, polarization states, and had persisted throughout their journey across cosmological distances and times. Now here's something that will really bake your brain. In 2019, physicists demonstrated a technique called quantum memory using photons. They could store quantum information in the photons, send those photons through optical fiber, and retrieve the quantum information at the other end with more than 95% fidelity. But what's crucial is that the information they stored wasn't classical bits, 0 south and 1 south, but quantum superpositions information in a form that cannot be copied or measured without disturbing it. This means we're now able to intentionally use photons as quantum memory devices, taking advantage of their natural ability to preserve quantum information over long distances and potentially long times. But here's where it gets practical in a way that should concern you. If photons naturally store quantum information so persistently, then they're also storing information about every photon-emitting device you own. Your phone screen, your computer monitor, your LED light bulbs, they're all creating photons that carry quantum information about their operation. And while that information becomes scrambled as the photons interact with the environment, it's not destroyed. In 2018, a team at the National Institute of Standards and Technology demonstrated that they could extract information about a laser's internal quantum state by analyzing the photons it emitted. They essentially read the quantum memory of the laser by carefully measuring its output light. This has implications for quantum cryptography, the supposedly unbreakable codes based on quantum mechanics, because it suggests that information can leak through photons in ways we're only beginning to understand. Let me give you a concrete example of how this works in practice. When you type on your keyboard in a dark room, photons from your screen reflect off your fingers. Those photons carry information about what was displayed on the screen at that moment. Most of them scatter into the environment and quickly become entangled with countless other systems, making the information effectively inaccessible. But in principle, if you could collect enough of those photons quickly enough and analyze them with sufficient precision, you could reconstruct what was on your screen. This isn't paranoid speculation. In 1985, researcher Wim van Eck demonstrated that you could reconstruct what was being displayed on a computer, monitored by detecting the electromagnetic radiation it emitted, including photons. Modern versions of this attack can work at distances of hundreds of meters under the right conditions. The quantum information in photons is more persistent and harder to scramble than we once thought. Every interaction leaves a trace, and while those traces become exponentially difficult to read as they spread and entangle with the environment, they're never completely erased. But now we need to confront something that might contradict everything I've just told you. Because while photons preserve quantum information remarkably well, there's one process that seems to destroy information. Measurement itself, or does it? Here's a question that's haunted physicists for a century. If quantum information cannot be destroyed, what happens to it when you measure a photon? Think about it. Before measurement, a photon can be in a superposition of multiple polarization states, simultaneously horizontal and vertical, for instance. But the moment you measure it with a polarizing filter, you get a definite result. The photon is either horizontal or vertical. So what happened to the information about it being in a superposition? Was it destroyed? For decades, this seemed like a fundamental paradox. The equation that describes quantum evolution, the Schrödinger equation, is perfectly reversible. If you know the quantum state now, you can calculate what it was in the past or what it will be in the future. No information is lost in this evolution. But measurement seems different. It appears to irreversibly collapse the superposition into a definite state, destroying information about all the possibilities that didn't manifest. In 1991, physicist Asher Pears made a crucial observation. Measurement doesn't destroy information, it transfers it. When you measure a photon's polarization with a filter, the photon becomes entangled with the trillions of atoms in the filter. The information about the photon's original superposition state isn't destroyed. It's now distributed across the quantum states of all those atoms. Think of it like this. Imagine you have a secret written on a piece of paper, and you tear that paper into 1,000,000 tiny pieces and scatter them across a football field. The information isn't destroyed, every letter is still there, on some piece of paper somewhere. But from a practical standpoint, the information has become inaccessible. This process is called decoherence, and it's the key to understanding why quantum effects seem to disappear in the macroscopic world. The quantum information doesn't vanish, it becomes entangled with so many environmental degrees of freedom that it's practically impossible to retrieve. But here's what will blow your mind. In 2011, physicist David Poulin at the University of Sherbrooke proved mathematically that decoherence is fundamentally reversible. If you could somehow control and reverse the states of all the environmental particles that became entangled with your quantum system, you could in principle recover the original quantum information, including the superposition that seemed to collapse during measurement. This has been experimentally demonstrated on small scales. In 2015, a team at Yale University managed to catch and reverse a quantum jump, the sudden change in a quantum system during measurement. They essentially undid the measurement, restoring the quantum superposition that had appeared to collapse. Now, let's apply this to photons specifically. When a photon enters your eye and is absorbed by a molecule in your retina, triggering a neural signal that eventually leads to your conscious perception of light, what happens to the quantum information the photon carried? According to everything we've discussed, that information is transferred to the molecule, then to the neural signals, then to patterns of brain activity. It becomes part of the vast web of quantum correlations that make up your brain state. The photon itself may cease to exist as a separate entity. Its energy is now part of the excited state of a molecule, but its quantum information persists in the system. Here's what should give you chills. Every photon you've ever seen has left a trace in your brain's quantum state. Not just a classical memory of seeing light, but a quantum entanglement between what was in that photon and what is now in your neural structures. You are, in a very literal sense, quantumly entangled with everything you've ever observed through light. But there's more. In 2019, physicist Vlatko Vedrol at Oxford published a paper exploring the idea that consciousness itself might be related to quantum information processing. While this is still highly speculative, his argument is intriguing. If consciousness is about integrating information in specific ways, and if quantum entanglement creates the strongest possible correlations between systems, then quantum effects might be essential for consciousness. This would mean that when you observe a photon, you're not just passively receiving information, you're becoming quantumly entangled with the history that photon carries, with every star it passed, with every atom it interacted with on its journey to you. Let me make this more concrete. In 2020, a team led by physicist Roger Penrose, who won the Nobel Prize for his work on black holes, proposed that microtubules in neurons might maintain quantum coherence for long enough to play a role in consciousness. While this remains controversial, if true, it would mean your brain is actively processing quantum information, including the quantum information carried by photons. Every time you look at a star, you're not just seeing it, you're becoming quantumly entangled with information from that star that has been preserved in photons for years, centuries, or even millions of years depending on the star's distance. But here's the truly profound implication. If measurement transfers information rather than destroying it, and if that information eventually becomes part of your conscious experience, then you are literally made of cosmic information. The quantum states in your brain right now are correlated with quantum states of particles throughout the universe, connected by the photons that have traveled from there to here. In 2016, physicist Václav Bruckner at the University of Vienna proved a theorem showing that quantum information in a closed system like the universe as a whole is strictly conserved during any measurement process. No matter how many measurements happen, no matter how much decoherence occurs, the total quantum information in the universe never decreases. It just becomes more and more spread out, more and more scrambled. So to finally answer our question about measurement, when you measure a photon, you're not destroying its quantum information. You're absorbing it. You're adding it to your own quantum state. You're becoming part of the universe's vast information network. And this leads to something truly beautiful. You're not separate from the universe, passively observing it. You're an active participant in the universe's information processing system, a node in a cosmic network of quantum correlations that spans all of space and time. But if this is true, if we're all connected through quantum information carried by light, then there should be observable consequences. And indeed, there are. What if I told you that your eyes can detect single photons, individual particles of light, and that this ability might rely on quantum effects that have been preserving information for millions of years of evolution? This isn't speculation. In 2016, a team of researchers led by physicist Rebecca Holmes at the University of Vienna conclusively proved that human eyes can detect single photons. Think about how remarkable this is. Your visual system is sensitive enough to respond to the absolute minimum possible amount of light, one quantum of energy. But here's what's truly mind-bending about this. Detecting a single photon means your eye is performing a quantum measurement. The photon enters your eye, is absorbed by a molecule called rhodopsin in your retina, and triggers a cascade of chemical reactions that eventually leads to a neural signal. That initial absorption event is a quantum mechanical process that preserves and transfers the quantum information the photon carried. In 2014, physicist Gregory Scholes at Princeton published groundbreaking work showing that photosynthesis, process by which plants convert light into chemical energy, relies on quantum coherence. When a photon is absorbed by a chlorophyll molecule, the energy doesn't just randomly bump around until it finds the reaction center. Instead, the system explores multiple pathways simultaneously through quantum superposition, finding the most efficient route. Think about what this means. Evolution has discovered quantum computing. Plants are using the same quantum principles that preserve information in photons to maximize their energy efficiency. The quantum information in sunlight is being read and processed by biological molecules that have evolved to exploit quantum effects. But it gets even stranger. In 2018, researchers at the University of Oxford discovered that European robins can sense Earth's magnetic field through a quantum process involving entangled electrons in molecules in their eyes. The mechanism works like this. When photons enter specific molecules in the bird's retina, they create pairs of entangled electrons. Earth's magnetic field affects these entangled states, and the bird can sense this effect. What's crucial here is that the birds are detecting quantum information that depends on both the photons they receive and the magnetic field they're in. The quantum states in their eyes are simultaneously entangled with both the light field and the magnetic field, a kind of quantum information fusion that evolution has optimized over millions of years. Now, here's where this connects back to our central question. If biological systems can read and process quantum information from photons, and if that quantum information has been preserved since the photons were created, then life itself might be part of the universe's information storage system. Consider this. Every organism that has ever lived on Earth has interacted with light. Photosynthetic organisms capture photons and convert them to chemical energy. Animals use photons to see. Even bacteria respond to light. Each of these interactions is a quantum measurement that transfers information from photons to biological molecules. And those biological molecules then pass that information forward through metabolism, through reproduction, through evolution. The quantum information that was once in photons becomes encoded in the structures of living cells, in DNA sequences that have been refined by billions of years of evolution, in the neural patterns of conscious brains. In 2017, physicist John Joe McFadden at the University of Surrey proposed that consciousness might involve quantum information processing in the brain's electromagnetic field. While highly speculative, his idea is that quantum coherence in neural firing patterns could create a unified field of information that corresponds to conscious experience. If he's right, then your consciousness is literally reading quantum information, information that has been stored in photons, transferred to your brain, and integrated into the quantum field that is your subjective experience. But here's what should truly blow your mind. DNA itself may be a quantum information storage system. In 2015, physicist Elisabetta Collini demonstrated that quantum coherence persists in DNA molecules for hundreds of femtoseconds, far longer than anyone expected. While this isn't long enough for DNA to function as a quantum computer in the conventional sense, it suggests that quantum effects play a role in how DNA stores and processes information. And here's the connection to photons. DNA is damaged by UV light through quantum mechanical processes involving photon absorption. But cells have evolved incredibly sophisticated quantum mechanisms to repair this damage. These repair mechanisms involve proteins that can recognize specific quantum states of damaged DNA and fix them with extraordinary precision. Think about what this means. Life has evolved quantum error correction. Your cells are constantly reading quantum information in your DNA, detecting quantum errors caused by photon absorption, and fixing those errors using quantum processes. You are a walking, breathing quantum information processing system that has been refined by billions of years of evolution. Let me give you a concrete example of how profound this is. When a UV photon strikes your DNA and creates a thymine dimer, a type of DNA damage that can cause cancer, a protein called photolase can repair this damage using a quantum process called quantum tunneling. An electron literally tunnels through an energy barrier that classical physics says should be impenetrable. The quantum information about the damage is read, processed, and used to guide a repair process that depends on quantum mechanics. You are not just passively affected by quantum information in light. You're actively processing it, storing it, and using it to maintain the complex information structure that is your living body. In 2020, physicist Matthew Fisher at UC Santa Barbara proposed that nuclear spins in calcium phosphate molecules in neurons might maintain quantum coherence for long periods, possibly hours or even days. If true, this would mean your brain can store quantum information in stable forms, potentially integrating quantum information from thousands or millions of photons over time. But here's the truly profound implication of all this. If life processes quantum information from light, and if that information can be stored in biological structures, and if those structures are passed down through generations via DNA, then the quantum information that was in ancient photons from the early Earth, from the young sun, might still be encoded in the structures of life today. You might literally carry quantum information from the dawn of life on Earth in the quantum states of molecules in your cells. Information that has been preserved, copied, and passed down through 4 billion years of evolution. The universe's memory doesn't just exist in abstract quantum fields or distant photons. It exists in you. Now we need to confront something that might seem to contradict everything I've told you about information being preserved forever. Why does time flow in only one direction? If quantum mechanics is reversible, if information is never destroyed, why can't we turn back time? This is called the arrow of time problem, and it's one of the deepest mysteries in physics. But the answer reveals something profound about the relationship between information and the nature of time itself. In the 1860s, physicist Ludwig Boltzmann realized that the second law of thermodynamics, which states that entropy always increases, gives time its direction. Entropy, roughly speaking, measures disorder. A broken egg has higher entropy than an intact egg. Smoke dispersed through a room has higher entropy than smoke concentrated in one spot. But here's the puzzle. The fundamental laws of physics, including quantum mechanics, don't distinguish between past and future. If you filmed a single photon interacting with an atom and played the film backward, you couldn't tell which direction was forward in time. The interaction works the same way backward and forward. So why do we only see eggs breaking and never spontaneously unbreaking? Why does entropy always increase? The answer, as Boltzmann realized, is statistical. There are vastly more high entropy states than low entropy states. Think of it like this. There are countless ways for an egg to be broken, all the pieces in different arrangements, but only one way for it to be intact. When things evolve randomly, they're overwhelmingly likely to move toward higher entropy states, simply because there are so many more of them. But here's where it connects to quantum information. In 2009, physicist Lorenzo Maccone at the University of Pavia proved something remarkable. He showed that the increase in entropy is fundamentally linked to the increase in quantum entanglement. As time passes, quantum systems become more entangled with their environments. This entanglement is what makes quantum information harder to retrieve. It's what makes the arrow of time. Think of it this way. When a photon is first created, it's in a relatively simple quantum state, minimally entangled with its environment. As it travels through space, it interacts with the quantum vacuum, with stray electromagnetic fields, with gravitational waves. Each interaction entangles it more with the universe. The information the photon carries doesn't disappear, but it becomes more spread out, more scrambled into the quantum state of the entire universe. This process is irreversible, not because information is destroyed, but because the universe keeps getting bigger and more complex. There are always more places for information to spread to, more systems to become entangled with. In 2018, physicist Carlo Rovelli published a provocative paper arguing that the arrow of time isn't a fundamental feature of the universe. It's a feature of our perspective as observers. We perceive time flowing forward because we're macroscopic systems that only interact with a tiny subset of the universe's degrees of freedom. From a God's eye view that could track every quantum state in the universe, time would be symmetric and reversible. But here's what makes this mind-bending. Photons, because they travel at the speed of light, don't experience time at all from their own reference frame. According to special relativity, if you could ride along with a photon, no time would pass for you between the photon's emission and absorption, regardless of how far it traveled. Think about what this means. A photon created in the core of the sun 8 minutes ago, from our perspective, and just now absorbed by your retina, didn't experience any time passing during its journey. From the photon's perspective, its creation and destruction are simultaneous. So the quantum information carried by photons exists in a kind of timeless state. It's only when the photons interact with matter, with atoms, with molecules, with your eyes, that they enter the time flow we experience. The information they carry is effectively frozen during their journey, preserved in a state that's outside our normal experience of time. But this raises a disturbing question. If photons exist outside of time, and if they store quantum information that cannot be destroyed, does that mean the information they carry is literally timeless? Does it exist in some sense at all moments simultaneously? In 2016, physicist Lee Smolin proposed a radical idea. What if time is more fundamental than space? And what if the laws of physics themselves evolve over time? In his view, the reason we have an arrow of time isn't just statistics. It's because time is the most basic feature of reality, and space and even the laws of physics emerge from temporal processes. If Smolin is right, then photons are messengers that carry information not just through space, but through the fundamental structure of time itself. The quantum information they preserve isn't just resistant to destruction. It's woven into the very fabric of temporal evolution. Now, let's connect this back to what we discussed about the holographic principle. Remember how information in a region of space is stored on its boundary? There's a time dimension to this too. In 1993, physicists Leonard Susskind and Gerard 't Hooft proposed that the universe's past, all the information about everything that has ever happened, is encoded on what physicists call the past light cone. Imagine a cone expanding backward in time from this moment, traced out by all the light rays that could have reached this point. Everything that could possibly have influenced this moment is on or inside that cone. And according to the holographic principle, all the information about those past events is encoded on the surface of that cone. Photons trace out this structure. Every photon that reaches you has traveled along the surface of your past light cone. The quantum information they carry is, quite literally, the information content of your past. But here's what will truly bake your brain. Because photons can be entangled across time as well as space, a phenomenon called time-like entanglement. The quantum information they carry can correlate events at different times. This means the universe's information structure isn't just three-dimensional or even four-dimensional. It's a complex web of quantum correlations that connects all points in space-time in ways that transcend our intuitive understanding of causality. In 2013, physicist Václav Bruckner demonstrated that you can have quantum entanglement between events that are causally disconnected, meaning neither event is in the past light cone of the other. This beyond causal entanglement suggests that quantum information creates connections in spacetime that don't respect our usual notions of cause and effect. Photons are the primary carriers of these beyond causal correlations. When two distant events both emit entangled photons, those photons carry information that correlates the events, even though they couldn't have influenced each other through normal causal processes. So to answer the question about the arrow of time, yes, time flows forward and entropy increases. But the quantum information carried by photons exists in a more complex relationship with time than simple forward flow. That information is conserved through time's passage, woven into the expanding structure of spacetime itself, creating correlations that transcend simple causality. You are not just moving forward through time. You're accumulating quantum information from photons that have traveled along your past light cone, information that connects you to the entire history of the observable universe. And that information will persist, carried forward by new photons, new quantum correlations, new webs of entanglement far into the future. Now that you understand how deeply quantum information is preserved in light, let's talk about what this means for technology, both present and future. Because humans are already beginning to exploit the universe's quantum memory in ways that would seem like magic a generation ago. Let's start with something that's operational right now: quantum cryptography. In 2017, Chinese researchers successfully sent quantum encrypted messages via satellite between Beijing and Vienna, a distance of more than 7,500 kilometers. The encryption was based on quantum key distribution, a method that uses the quantum properties of photons to create unbreakable codes. Here's how it works. You send photons in specific quantum states, say, different polarizations to represent bits of your encryption key. If anyone tries to intercept and measure these photons, the measurement inevitably disturbs their quantum states due to the no-cloning theorem we discussed earlier. You can detect this disturbance and know that someone was eavesdropping. But here's what's truly remarkable. The security of this system depends on the fact that quantum information cannot be copied or measured without leaving a trace. It's not that we haven't invented good enough eavesdropping technology. The laws of physics themselves make it impossible to intercept quantum information without detection. This is already being used for securing financial transactions, government communications, and military operations. The quantum memory of photons, their ability to maintain quantum states over long distances, is literally protecting some of the world's most sensitive information right now. But the implications go much deeper. In 2019, Google announced they had achieved quantum supremacy, performing a calculation on a quantum computer that would be practically impossible on a classical computer. While Google's quantum computer uses superconducting circuits rather than photons, photonic quantum computers are rapidly advancing. A photonic quantum computer uses photons as qubits, quantum bits that can be in superpositions of 0 and 1 simultaneously. Because photons naturally preserve quantum information so well, they're ideal for building quantum computers that can operate at room temperature without elaborate cooling systems. In 2020, a Chinese team led by physicist Qianwei Pan demonstrated a photonic quantum computer that achieved quantum supremacy using boson sampling, a specific quantum task that's exponentially harder for classical computers. Their computer used 76 photons and could perform calculations that would take a classical supercomputer hundreds of millions of years. Think about what this means. We're now building computers that exploit the same quantum information preservation properties that the universe has been using for 13.8 billion years. We're learning to read and write to the universe's memory directly. But here's where it gets really wild. In 2018, researchers at the University of Vienna demonstrated quantum memory using photons trapped in crystal lattice. They could store a photon's quantum state in the crystal, then retrieve it later with high fidelity. They essentially created artificial atoms that can catch photons and hold on to their quantum information. The longest storage time they achieved was about 1 second, which might not sound impressive, but in quantum terms, it's an eternity. A second is enough time for light to travel to the moon and back. During that second, the photon's quantum information, including delicate superposition states and entanglement with other photons, was perfectly preserved. Now extrapolate this technology. What if we could create materials that trap and store photonic quantum information for hours, days, or years? We could build quantum memory banks that store information in a fundamentally more secure and dense format than any classical computer. But the really mind-bending applications are still theoretical. Physicist David Deutsch, one of the pioneers of quantum computing, has proposed that quantum computers could be used to simulate other quantum systems with perfect accuracy. This means we could, in principle, simulate the entire evolution of quantum states in the early universe, reconstructing information that seems lost to us now. Think about what this means. If the universe is a quantum system, and if quantum information is preserved in principle, even when it's practically inaccessible, then a sufficiently advanced quantum computer might be able to retrieve information from the universe's past by simulating the quantum processes that scrambled it. This isn't time travel. You're not sending information backward in time. But you might be able to reconstruct what happened in the past by exploiting the fact that quantum evolution is reversible. You'd be reading the universe's memory by running the cosmic quantum computation backward. In 2016, physicist Seth Lloyd proposed using quantum computers to study black hole information paradoxes by simulating the quantum evolution of matter falling into black holes. While we can't build real black holes in laboratories, we might be able to simulate them quantum mechanically and verify whether information really is preserved. But here's something that should concern you. If we're developing the ability to read quantum information from light, then we're also developing the ability to extract information that people thought was private. Remember how I mentioned that photons from your screen carry information about what's displayed? As quantum technology advances, the ability to read such information will improve. In 2020, researchers demonstrated that they could use quantum illumination, a technique that entangles the photons you send to scan an object with photons you keep in your detector to see objects in bright light that would normally be invisible due to noise. This works because quantum correlations between the photons persist even in noisy environments. This technology is being developed for radar systems that can detect stealth aircraft. But the same principles could be used to extract information from quantum states of light in ways we can't do now. As our ability to manipulate and read quantum information improves, the line between what's private and what's accessible will blur. But let's end this section on a more inspiring note. The same quantum properties that make light preserve information so well could revolutionize communication. Quantum Internet a network that transmits information using entangled photons would be fundamentally more secure than current Internet and potentially allow for distributed quantum computing where multiple quantum computers share quantum information seamlessly. In 2021, researchers in the Netherlands created the first prototype quantum internet link using entangled photons sent through fiber optic cables. While rudimentary, this proves the concept works. Within decades, we might have a global quantum internet where information is transmitted via photons in quantum states that preserve perfect security and enable new forms of computation. You're living at the dawn of the quantum information age. The same principles that the universe has used to store information since the Big Bang are now being harnessed by human technology. We're learning to read and write in the universe's native language, the language of quantum states preserved in light. Now, I need you to stop and really think about what all of this means for you personally. Not abstractly, not theoretically, but right now, in this moment, as you watch this video. Every photon entering your eyes from this screen right now is part of the universe's quantum information network. These photons were created by electrons and LEDs or pixels, underwent quantum state changes to encode the image you're seeing, traveled through space, passed through your pupil, and are now being absorbed by rhodopsin molecules in your retina, triggering quantum mechanical processes that generate neural signals that become your conscious experience of vision. That's not a metaphor. That's literally what's happening. You are a quantum information processing system interfacing with other quantum information processing systems through the medium of light. But here's what should fundamentally change your worldview. Every photon you've ever seen, from every sunrise you've watched, every star you've gazed at, every screen you've stared, has left a quantum trace in your brain. You are, in a very literal physical sense, constructed from information carried by light. Think about your memories of visual experiences. When you remember seeing a sunset, you're accessing neural patterns that were originally created by photons from that sunset. Those photons were created by nuclear fusion in the sun, traveled 93 million miles through space, scattered off molecules in Earth's atmosphere to create the colors you saw, entered your eyes, and became part of you. A quantum information in those photons information about the nuclear reactions that created them, about the magnetic fields in the sun, about the atmosphere they pass through, is now woven into the structure of your brain. You carry the sun's quantum signature within you, but it's more profound than that. Remember what we learned about entanglement. Quantum systems that interact become correlated in ways that transcend space and time. When photons from a distant star enter your eye, you become quantumly correlated with that star. There's now a quantum connection between you and that star that persists even after the photons have been absorbed. You are not separate from the universe, observing it from outside. You are a node in a vast network of quantum correlations that connects everything in the observable universe that has ever interacted through light. You are, quite literally, entangled with the cosmos. In 2019, physicist Carlo Rovelli published a beautiful paper about the nature of reality from the perspective of quantum mechanics. He argued that objects don't have properties independent of their interactions. They only have properties relative to other systems they interact with. A photon's polarization is only defined relative to the measuring device. Your perception of color is only defined relative to your visual system. What this means is that reality is fundamentally relational. You don't perceive an objective universe that exists independently of you. You perceive your quantum correlations with the universe. The redness of a rose exists in the quantum relationship between photons, rose molecules, and your visual cortex. It's not in any one of those things separately. This isn't philosophical wordplay. It's the literal implication of quantum mechanics. The universe you experience is the universe as it relates to you, a unique perspective created by your specific quantum correlations with everything you've interacted with through light and other means. But here's what should fill you with awe, because quantum information is preserved. Your quantum correlations with the universe are permanent. Every star you've looked at, every sunrise you've witnessed, every person whose face you've seen, you carry permanent quantum correlations with all of them. They're part of your quantum state, and you're part of theirs. You are not a temporary, isolated consciousness briefly sparking into existence and then vanishing. You are a pattern of quantum correlations that has been built up over your entire life through your interactions with light and matter, and those correlations will persist in the quantum state of the universe forever. When you eventually die, your consciousness will end, but the quantum information that made you, the patterns of entanglement, the correlations, the information structure will remain encoded in the universe. Some of it will be in light photons that bounced off you and are now traveling through space. Some will be in the atoms that were part of your body. Some will be in the brains of people who knew you, accessed through memories triggered by light-based visual experiences of your face. You are not meaningless in a vast, uncaring universe. You are a unique node in the universe's information network, a one-of-a-kind pattern of quantum correlations that has never existed before and will never exist again, but whose influence on the quantum state of reality is permanent. Let me make this more concrete. Right now, as you watch this video, photons from the screen are entering your eyes and creating new neural patterns, new memories, new quantum correlations in your brain. These correlations are literally changing the physical structure of your brain, strengthening some synapses, weakening others, creating new patterns of connectivity. These changes persist. Tomorrow, next week, years from now, you'll carry the quantum information from this moment forward. And when you act on that information, when you tell someone else what you learned, when you look at light differently, when you make different choices, because of how this video changed your worldview, you'll be propagating the quantum information forward, spreading it through the network of human consciousness and technology. In a very real sense, ideas are quantum information patterns that propagate through networks of human brains using light as the primary medium. Every book you read, every video you watch, every conversation you have with someone where you make eye contact, these are quantum information. Transfer events that change the structure of your brain and create lasting quantum correlations.